We're going to be covering DistAI, which is a data-driven automated invariant learning for distributed protocols. Cool. So I'm going to cover just a couple pieces of terminology that I wasn't like as familiar with as I should be. I hope this isn't too boring for everyone else. So an invariant is a formula about the system state that is always true. It's used in like distributed systems analysis and also used in like a micro level kind of like program analysis too. And then an inductive invariant is something that's like broadly trivial to prove in the solver that we're going to be talking about a lot. And it has the following properties: that its initial statement is true, and all subsequent changes to the state will remain true, or at least in So it's kind of like, it's like a proof by induction essentially on an invariant. Cool. So we're going to be talking about Ivy throughout this, and Ivy is a tool for specifying, modeling, implementing, and verifying protocols. And an example of a protocol would be something like Paxos, would be a protocol for distributed consensus. And there's a lot of like much simpler protocols like a distributed lock or what have you. And essentially in Ivy, I can write that down in something approaching like a programming language but without sort of like the full like nuts and bolts implemented, if that makes sense. So it's sort of like you would define a set of functions that you export, and then Ivy will apply, like basically change the variables inside of that and like run those functions in order based on the invariants that you've given it. And it will basically will try and solve for the space that you give it. But it's not like if you'd implemented Raft in Java or something. It's not like a functioning thing. It's a description of the problem. Cool. So at a high level, basically what DistAI does is it gives you the ability to to basically prove the correctness of a protocol in monotonic and finite time. So like the solver so essentially it runs monotonically in finite time. So it's essentially like the guts of it, and what makes it special versus the surrounding literature is that it won't run forever on any problem, and it will always provide you an answer. It can't necessarily solve for all protocols, but it will always exit, and it does, and essentially it searches the space of possible solutions monotonically. So and that just means basically that for any search, like the next value is either equal to or less than, essentially. So it's like you're going down this graph, and it can like plateau, but it'll eventually always go down. That makes sense. Cool. So its goal essentially is to find an inductive invariant from a set of invariants, and essentially the inductive invariant will be the result of applying at one or more invariants to the safety protocol. So essentially you specify something like a statement that guarantees the safety of your protocol. And what this will do is it will find a set of invariants for your protocol such that it will convert that safety protocol to an inductive invariant. So we want this inductive invariant because, as we said earlier, you can trivially prove that an inductive invariant would provide correctness. So we select invariants to check by ascending order of the number of variables, and we filter to discard invariants that imply other invariants. So you can kind of think of a lot of what DistAI does as like a very clever way to search the space of invariants. So rather than searching all possible invariants, what DistAI does is it attempts to narrow the set of invariants you have to check, and with the assumption that I maybe should have stated earlier that when you check an invariant, that's quite an expensive and slow process. So so essentially what a lot of what DistAI does is essentially, yeah, basically just like lessen the space that you have to search to find the invariant that converts your safety protocol to an inductive invariant or set of invariants that will do that. So it only looks at universal invariants. I didn't dig too deep into like the different types, categories of invariants, but a universal invariant is essentially one that applies to everything, all the nodes in the system, and it isn't specialized to any subset of the protocol, is what I roughly understood. So it describes itself as data-driven because what it does is it generates a set of data, and then it takes these subsamples of that data. And the data in this case would be kind of like a set of nodes. So like you might have like 100 nodes, and then it would basically take subsamples of that to try and prove invariance about the system. Cool. Okay, so this is like the workflow diagram that they specified in the paper. Essentially, the system works by having three stages that are so directly implemented by the authors. So it takes the whole system takes as input a distributed protocol. It does this two-stage sampling step. Then it provides a set of subsamples from that sampling to the enumeration stage. And what the enumeration stage does is it finds a set of invariants that you want to check in Ivy. So essentially, the sampling step is what like gives you the data to try and find like a good set of invariants to then provide to Ivy, and Ivy will then check this best case collection of invariants. And if the invariants fail, like one or more invariants fail, it will throw it back to this thing called the monotonic refinement. And that's kind of like really I think from what I understood, that's kind of like the special secret sauce of DistAI. And essentially what it does is it takes the set of failed invariants and then weakens them. So what the enumeration step will give you is like the strongest invariant it can find. So it's the kind of like the from what I understood of like strong versus a weak invariant, it's just like a strong invariant will be harder to prove than a weak invariant. I could be wrong about this, but like that's roughly from what I understood. So by diluting the invariant, we know that we are searching the full state space. So we'll start out with like the strongest invariants, and then we'll gradually loosen them. So we are kind of like decreasing the space we're looking at, and at the same time we know that we're searching the full space. So that's how DistAI is basically guaranteeing that it will definitely search the full space, and it will do so in this kind of like this decreasing level of strength. So it will like monotonically refine basically, and the monotonic refinement is the refinement of the set of invariants that you need to look at. So when it finds these weakened candidate invariants, it pipes them back into Ivy to see if that will basically solve this protocol. If it's unable to do that and the safety property fails, it pipes back essentially the failures to the sampling stage, which will then sort of like we'll make different decisions about what it will then propagate down into the enumeration stage. So we're just like gradually decreasing the space we're looking in so that we know we can exit either successfully or with a failure. So that's kind of like that's getting us the special ability to actually exit, unlike other solvers. So this is like, I might be getting too deep at this point into something that I probably don't understand totally well enough. But we simulate the protocol on different sizes of systems, storing changes in the system state. We then project these samples into subsamples based on the formula size, so that you might have a formula with like 4 or 5 variables in it, and those variables are basically what the solver is going to change when it looks at whether or not your invariant will hold. So enumeration will then take these samples, as we mentioned, and get the strongest candidate invariants, and then hand them off to IV. IV, if it fails, as we mentioned earlier, we'll pass it back to the monotonic and refinement. Or if it succeeds, we will like say we've solved this protocol and here's a set of invariants that solves this. Awesome. Okay, so we have this like set of sampling parameters. They don't actually affect at all whether or not the inductive invariant will be found, but it changes the speed at which we find it. So so we have like this like maximum number of instances we want to consider before we terminate. We have the maximum number of instances considered before terminating if no further subsamples are generated. And we have the number of actions to take when simulating a finite instance, and the number of subsamples to generate from one data sample. Yeah, I'm sorry if I'm losing people here, but yeah, the rough idea is that we convert IB representation to basically multi-dimensional Python representation of the protocol. We then create a set of valid initial states that are limited in size so that it doesn't get insane in terms of like runtime. And then we do up to MA. So that's this maximum number of instances to consider before terminating. So we do up to the maximum number of instances to consider before terminating. Randomly selected actions are then performed on each initial state. So this is kind of, I guess, where the AI component comes in. So we have like this stochastic property where we're starting at these randomly generated sampled states. So then for this next step, we return back these generated states. And then we subsample them. So we find a small set of subsamples that we randomly choose, and that's defined by SD, the number of subsamples to generate from one data sample. So we take this random set of subsamples and we terminate when we have sampled the maximum number of samples, or when no new subsample is found after simulating the maximum number of consecutive instances of the protocol. Cool. So then we step into our enumeration stage, where we break apart the space of invariants, and then we enumerate all possible invariants in each area, like subspace that we've generated by partitioning. We discard invariants that do not hold for the samples we collected, and that's how we're data driven. So by collecting these samples, we're able to discard some of the invariants because they just won't fit, if that makes sense. we discard any symmetric invariants. So it's like if you can, yeah, if the operator is symmetric and we can flip them to either side, we don't actually care about, we only need one of those essentially, if that makes sense. So we filter them. We try to match invariants to the smallest subspace they can evaluate against so that it will be faster when we evaluate. And then we collect all the remaining invariants for each subspace, and we basically union everything together into one big set. And then we discard all invariants that are implied by another invariant. So so essentially we're just continually, so we have this randomness earlier on where we're generating kind of like a random set of invariants, and then we're pruning down to like this minimal set of invariants that we need to check. So we feed Ivy this union of minimal set of invariants with the safety property, and then we go through this monotonic refinement process where we gradually refine down to this perfect set of invariants that convert our safety property to an inductive invariant and can therefore prove the correctness of the protocol. Okay, cool. I'm running low on time, so I'm just going to jump into evaluation. So basically, they found that DistAI would complete correctly for 13 of the 14 protocols they checked. The other implementations, so like I4 and FOL-IC3, either would not complete in finite time or would complete incorrectly. So it was a massive jump in terms of what was provable, and a significant jump in terms of speed. I think it was at least 50% faster. And for Paxos, no one was able to solve it because there's a type of invariant that's just not possible, that's not supported by DistAI, that you require to be able to actually prove the safety protocol for Paxos. Yeah, so it's like basically my presentation. I'm sorry, it's really a little bit gobbled. Definitely not an expert in this space, but I think in summary, the basic idea is that we stochastically we have the stochastic process at the start of to find invariants. So we kind of like randomly search inside of the space, and then we prune the space as we work. So we don't search every single possible option in like the best case, and we also are able to guarantee that we're constantly refining and decreasing the space of invariants we're searching inside of, to then so that when we apply those invariants to the safety protocol, we're guaranteed to find either something or nothing, and we should never miss a possible solution. But at the same time, we don't actually have to check every single possible combination of invariants, because we have a lot of like clever pruning of the possible set of invariants. And I guess like the really core thing to remember is that like the cost of checking a set of invariants plus a safety protocol is very expensive. So a lot of the reason DistAI is a lot faster is that it has a lot of like clever tricks that it uses to prune the set of invariants it actually has to check against the safety protocol. But it still does this in a safe way where we will always be able to find the set of invariants if they exist to prove that that safety protocol is safe. Okay, cool. Thanks so much for listening to me ramble. Really appreciate it. I'll hand it back.